Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 4 Chemistry students. Welcome back. I believe you're safe and healthy. Alan is my name, still with you in chemistry lessons. So we are still on topic 3, the periodic table, but we are focusing on unit 12 still, which is about the chemistry of group 7 elements, sometimes called 17. It's okay, they can all work. Then we now on lesson 3, which is about the chemical properties of group 17 elements. I named it part 2 because we are continuing from lesson 2, which was also about the chemical properties, but in this case we shall be looking at different properties compared to what we looked at in the previous lesson. So, a quick recap on what we looked at in the previous lesson. We looked at oxidizing ability and the reducing powers of group 7 atoms and halides respectively, whereby we looked at the fact that when halogen atoms gain electrons or gain an electron, they are exhibiting oxidizing power. And when the halide, that is the atom has already gained an electron forming a halide or an anion, the anion can lose the electron in presence of an oxidizing agent. So we used an example of sulfuric acid to check the reducing strength of the halide ions, as you can see on our slide. So this is exactly what we looked at. This is a summary or a review. We can quickly check it up. So the point here is the chloride ion in the potassium chloride is a poor reducing agent, so it only reacts with acid-base reaction in presence of sulfuric acid, forming the fumes. As we saw, these are the fumes tested using ammonia. Then the bromide in potassium bromide is a relatively stronger reducing agent, so it will reduce the sulfur in sulfuric acid from positive 6 to positive 4 as it is being produced as a sulfur dioxide gas. And we looked at its test, as you see the illustration over there. Whereas iodide in potassium iodide is a strong reducing agent, so for it, it reduces the sulfur in sulfuric acid from positive 6 up to negative 2, as you see, depending on the product, whereby we see or we saw the yellow salt, as you see here, that is for sulfur. Then even the sulfur dioxide gas tested using the dichromate solution. This is the illustration. And the hydrogen sulfide, as we noticed in our demonstration. So the point here is, as down the group, the halides, they are reducing strength, increases, reducing the sulfur and sulfuric acid to different products, basing on their reducing strength. So that is what we looked at in the previous lesson, and we can now move to today's content, lesson 3. So we are still looking at the chemical properties. I called it part 2. It is an additional. So in the previous lesson, we looked at the oxidizing powers and the reducing powers. This indicated in light in pink color. So today we're going to focus on displacement reactions and other reactions like reacting a halogen with water, alkalis, and so on. So this takes me to highlight on the objectives. Lesson objectives. Again, of course, the objectives will be coming from the content we had covered, which are these two, displacement reaction and the other normal reactions of the halogens. So I expect by the end of the lesson, you should be able to, one, relate and explain the oxidizing abilities of the halogen, two, their displacement reactions of the halide ions. Compare what we looked at in lesson 2 with the displacement reactions in this lesson. Then compare the products of the reactions of the halogens with the dilute and concentrated sodium hydroxide. That is basically the alkali. We shall only be focusing on sodium hydroxide. But there are other alkalis like calcium hydroxide, which we shall bring towards the end of the lesson. So these are the two objectives we shall focus on in details. Now let's go to the chemical property number 3, that is adding on oxidizing ability, reducing ability. Now we are on the displacement reaction. So what we need to know is this reaction clearly gives us a combination of all the two properties we looked at before. The oxidizing ability of the halogen atoms and the reducing abilities of the halide ion. In this case, we are combining all of them. Then, so a point to note before we get started is when you get oxidizing and reducing all combined, we have what we call a redox reaction. So in this case, we are going to see that the strongest oxidizing agent normally displaces the strongest reducing agent. Before we actually see how it happens or see the demonstration, let me clarify something in here. Halogen atoms are oxidizing, indicating they attract and they accept an electron. And when they accept it, they form a halide ion. So that halide ion, because of the big size, it can lose the electron that it had gained. So that is what we mean. Bring, for instance, chlorine, which is highly oxidizing. It will make bromide lose electrons. So it will displace a bromide, forming bromine gas. Then bromine will displace iodide, but not the chlorides, and so on. So before we do the demonstration, remember the colors. You see these colors. You need to have this knowledge for you to understand the whole displacement reaction. Let's see the demonstration. Okay, so we're now going to have the solutions of each halide in their respective, in these beakers. So we're having one set, chloride, bromide, iodide, another set, the same thing. The set we have at the first is the set we have the second, and the set we have the third. So we are going to add chlorine water in all of them. Take a close look what happens. We've added chlorine water there, then we add bromine water. Next, we add iodine water. The iodine, bromine, and chlorine water are just bringing the molecular halogens, or their molecules. Remember, we are looking at the displacement reaction, whereby we have the molecule reacting with the halide or the ion. So the next step, we are to add a solvent. Since these are covalently bonded, then we use a non-polar solvent. It will clearly show us the presence of each component when the reaction ends. The solvent you're using is cyclohexane. We're adding it throughout in all. You're already seeing some of the observations, the color changes that are happening. When that is done, we need to shake a little bit so as the reaction can take place. We shake for a few seconds, then we observe what will happen. You're already seeing some of the observations. Now, it is time to observe. What do we see? What do we exactly see? Take a close look and discuss with a friend if you're having a friend nearby you. Now, the next is we need to now explain and describe what we are seeing, then relate them to the oxidizing abilities. There we are. These are our observations. You noticed what happened. We added chlorine solution, or what we call chlorine water, into a test tube of chloride, bromide, and iodide. At the same time, we added bromine water into a test tube of chloride, bromide, iodide, and even we did the same for iodine. Take notice, we still have our color in presence of a non-solvent, a non-polar solvent. So let's start from the side of chlorine. Where we have chloride and chlorine water, no observable change. It is still colorless solution. Where we added chlorine water to the bromide, we are having the orange solution on top. So we are having the bromine being formed. Where we added chlorine in the iodide, we are having the purple. This deep blue you're seeing, that is the purple part of iodine. Look at test tubes of bromide, of chloride, bromide, iodide, in addition of bromine. For chloride and bromide, we see they are actually similar, indicating there is no difference in there. We have the orange solution on top. Then for the iodide, it is turning to purple, similar to one of chlorine water. Lastly, where we added the iodine water, we're seeing the purple or the violet solution, indicating it's just the iodine in it. Remember the color changes in here. So let's conclude from this observation. What do we conclude? When you react chlorine with the bromide and an iodide, what happens? The bromine is displaced from the bromide ion. In other words, the bromide loses electrons. The electrons are gained by the chlorine to form a chloride, which is a colorless in this case, and the bromine as a molecule. And the presence of cyclohexane, it makes it appear as orange, as you see the orange color. Look at this illustration. You see the orange color. What happens to the iodide? Chlorine displaces iodine from the iodide solution. And so we are having that purple solution being formed. It's because of the iodine. So chlorine displaces both bromide and the iodide from their solution, forming their respective molecules. What happens if we have bromine reacting with the chloride and the iodide? We see, this is what we actually observed. Orange, orange, then purple. What is the reason behind it? When you add bromine to a chloride, the orange color still persists, indicating we do not have the chloride being displaced, or we do not have the chlorine being formed. In that way, there is no reaction. Since the chlorine is a strong oxidizing agent, it can't be displaced by bromine. Look at the iodide. Look at the iodide. It turns to purple. Simply, it is being displaced by the bromine, since bromine is more oxidizing than the iodide. Lastly, look at the reaction with iodine. Actually, there is no reaction that occurred because we still have the violet or the purple solution. That is iodine, which was added in. Remember, it was added in the colorless solution, so we still have the iodine, indicating there was no displacement taking place. So that is what happens when it comes to the displacement reactions. That is what happens when it comes to the displacement reactions. The more oxidizing displaces the less oxidizing. Something we need to note in here. Fluorine, actually being the most oxidizing, we expect it to displace all the halide ions. But because it is poisonous, we do not normally carry out any tests for it. Because it is actually poisonous, it requires a well-equipped laboratory. So we do not carry out its reactions in a normal setting. So that is with displacement reactions. Now let's look at the other chemical properties, and in this case we shall be looking at reaction with water, alkalis, and hot phosphorus. So, but before we look at those reactions, one unique aspect, as we mentioned before, fluorine is actually very unique. It's a unique member in the group. So due to its small size and the high nuclear charge, fluorine has high oxidizing powers and high electronegativity. And as such, for it to react differently. Some of the properties in which it differs from the rest of the group members are, most of its compounds are ionic. We actually looked at aluminum chloride, which was covalent. We also looked at lead chloride, which is covalent, lead 4 chloride, which is covalent, whereas the ones for fluorides are ionic because of its high oxidizing power and electronegativity. So it takes electrons from other atoms. 2, its compounds are inert because you don't have any other atom that can displace fluorine from its compound. We just looked at displacement reaction. So for fluorine, since it is the most oxidizing, there is no any other atom that can displace it for one to form the fluorine molecule. So lastly, it forms hydrogen bonds. It is the only atom in group 7 which forms hydrogen bonds with hydrogen. The rest do not. So with that background, let's see some of the reactions. Again, in each reaction, we have to look at fluorine differently from the rest of other halogens. So first reaction with water, fluorine, when it reacts with water, it forms hydrogen fluoric acid and oxygen gas. In this case, the oxygen loses electrons to the fluorine. Remember, it is the most electronegative, at the same time, the most oxidizing element. So it takes electrons from the oxygen, depositing oxygen. In simple, you can say fluorine displaces oxygen from water. So the others react differently under a disproportionation reaction to give different products. The focus here is on disproportionation reaction, whereby one of the species in a reaction is both oxidized and reduced at the same time. Let's use the example of bromine, for instance. When you react it with water, it forms hydrogen bromide, or what we call hydrogen bromic acid, and the bromine water, HOBr. We shall see the use of bromine water. But the focus now is on disproportionation reaction. As a molecule, bromine has oxidation state of 0, meaning the atoms involved in this molecule have same electronegativities, so electrons are equally shared. So when it forms hydrogen bromide, the hydrogen has lower electronegativity, so it will gain an electron from hydrogen, and so it has oxidation state of -1 after gaining an electron. Whereas in this bromine water, or what we call the hypobromous acid, the presence of oxygen, which is more electronegative, makes bromine lose electron to oxygen, as you see in here. So its oxidation state becomes +1. In this case, we have bromine being reduced because it gained an electron in the H bromide, and being oxidized because it lost an electron in HOBr. That is what we call disproportionation reaction. So we talked of bromine water. This is the color of bromine water. That is orange, and it is used in chemistry for confirming the presence of carbon-to-carbon double bonds. You're going to see this when we reach more in organic chemistry, possibly in senior 5. So that is reaction with water. Again, take note, fluorine reacts differently from the other halogens because of its high oxidizing power and negativity due to its small size and high charge. So let's look at reaction with alkalis. First with fluorine, since it is unique. And the products here depend on whether you have a cold and dilute alkali, or it is hot and concentrated. If it is dilute and cold, then different products are given out in regard to when it is concentrated and very hot, as you see those products. Let's look at the other halogens. What happens? Again, we're bringing in the word disproportionation. The point to take in here is with cold dilute alkalis, a halide is formed and a halate one. What do we mean by the halate one? I'll use this example with the chlorine. Get chlorine gas, react with the dilute sodium hydroxide, you will form sodium chloride and sodium hypochlorite. This is called sodium hypochlorite, and it's what we call as a halate one. So, again, this proportionation, in sodium chloride, the chlorine gains an electron from sodium. So it is being reduced. It has oxidation state of -1 after gaining. But the presence of oxygen here, which is more electronegative, makes chlorine to lose an electron. So we are having chlorine existing in +1 oxidation state. That's why it is called halate 1. So, and this sodium hypochlorite, it is a disinfectant and a bleaching agent. It's normally used in industries and even in normal pharmaceutical labs and so on. The last reaction on this part is when we're having hot and concentrated alkalis. Still using the chlorine, The difference in here is we are forming a halate 5. Halate 5 simply because the chlorine is in the oxidation state of 5. That's why it is called, for instance, chlorate 5, or the halogen is in oxidation state of 5 called halate 5, compared to halate 1, oxidation state of positive 1. So example here is, as I said, sodium chlorate, which is also a bleaching agent. So let's look at the hypochlorous and the hypochlorite. What you need to know is when you react these halogens in water, they form as simple hydrogen halide and sometimes hypohalous acid, which when it ionizes, it gives what we call the hypohalite ion. Example here is the hypochlorite in presence of chlorine. This is actually a good oxidizing agent, and that's why it is used in much of the oxidizing or disinfectants. For instance, calcium hypochlorite and sodium hypochlorite. So its use is it's used in water treatment centers and swimming pools. They normally add that component in there. You see it is an oxidizing agent, so it kills all the microbes. Lastly, we are ending with reaction with phosphorus. Simple. Get a halogen, heat it in a limited amount of phosphorus, then you will get phosphorus trihalide, depending. If you have like chlorine, then it becomes phosphorus trichloride. If it is for bromine, it becomes phosphorus tribromide. And in excess, it forms a pentahalide, like phosphorus pentachloride, and so on. So that is it for today. I will have to leave you with the exercise, which I call exercise 3. And it is clearly seen. So the question number 2 reads, chlorine is one of the reagents used in water treatment to make it safe for drinking and home use. Write a balanced equation for the reaction of chlorine with water. Explain how exactly chlorine makes water safe for drinking. So go through what we looked at. If you understood well, this question should be easy for you to attempt. That is it for today. Stay safe.